You ever wonder how 1,000 people don't book the exact same airplane seat at the exact same time? It's not magic, it's this fundamental idea in computer science called mutual exclusion. And today, we're going to break down exactly how it keeps our digital world from falling into total chaos.
I mean, seriously, think about it. Every time you buy a concert ticket or like a photo or do pretty much anything online, there are all these different servers that have to agree on who gets to write the new information first. So how do they do it? How do thousands of independent computers work together on one thing without just corrupting all the data or tripping over each other? That's the big question we're tackling.
So the answer is a concept called mutual exclusion. At its heart, it's just a rule that says only one process at a time can be in the critical region. That's just the fancy term for the piece of code that's touching the shared data. It's basically a one-person-at-a-time rule for a digital room, and it is absolutely essential for making sure data stays consistent and reliable.
Okay, so if we're gonna solve this problem, any system we come up with has to follow a really strict set of rules. And these are not just suggestions, they are the absolute bedrock for any solution that's actually gonna work. You can think of them as the rules of the game.
First up, safety. One process in the critical section at a time. Period. No exceptions. Next, liveness. If you ask to get in or get out, it has to happen eventually. The system can't just hang forever. Third, order. It's got to be fair, right? So first come, first served. And finally, no starvation. This means no single process gets stuck waiting forever while everyone else gets to go.
So how do we actually meet all those rules? Well, the first approach is probably the one you'd think of first. Let's just put somebody in charge. This is the central coordinator algorithm. Simple, right?
The logic here is just so beautifully simple. A computer wants in, so it sends a request to the boss, the coordinator. If the coast is clear, the coordinator shoots back a grant message. If it's busy, the request just gets put in a line. And once the computer is done, it sends a release message, and the coordinator just lets the next one in the queue have a turn. It's kind of like asking a barista for the only key to the coffee shop's bathroom.
And this diagram shows you exactly how it works. So in panel A, you see process 1 asks the coordinator, which happens to be process 3, for permission, and boom, it gets it. Then in B, process 2 asks for its turn. But since 1 is still in there, the coordinator just says, hang on, and queues the request. Finally, in C, process 1 is done, it sends its release, and now the coordinator can give the green light to process 2. See? Super simple, super orderly.
But this brings us to the big trade-off. On the one hand, this approach is great. It absolutely guarantees mutual exclusion, it's fair, no one starves, and it's pretty easy to build. But, and this is a huge but, the shortcomings are really bad. The coordinator is a single point of failure. If it goes down, the entire system grinds to a halt. It can also become a performance bottleneck. And maybe worst of all, a process has no way of knowing if the coordinator is just busy or if it's totally dead.
And from a network standpoint, it's actually really efficient. It only takes 3 messages for the whole cycle: 1 request, 1 grant, and 1 release. Keep that number 3 in your head because it's going to be a really important benchmark for what comes next.
Okay, so that single point of failure, that's a deal breaker. So what if we just get rid of the boss? Let's try something more democratic, where everyone gets a vote.
So here's how this one works. When a process wants access, it sends a request message with a timestamp to every other process in the system. It's kind of like sending a group text to plan a surprise party. You got to get a yes from every single person before you book the venue. Everyone else votes by replying OK if they're not using the resource. And if there's a tie, the process with the earlier timestamp wins. You only get to go in after you get an OK from everybody.
This diagram shows us exactly how that tie gets broken. So in part A, you can see processes 0 and 2 both want in, and they send out requests with timestamps 8 and 12. Then in B, because 0's timestamp is lower, it wins the vote and gets into the critical region. Process 2 has to wait. Once 0 is done, as you can see in C, it sends an OK over to 2, which can finally get its turn.
But here's the massive catch. Yeah, we got rid of the single point of failure, but we replaced it with n points of failure. Now, if any single process crashes, it just stops responding. And that means everyone else is just sitting there, waiting for an OK that is never going to arrive. The whole system gets blocked. It's way more complicated, way more expensive, and honestly, not nearly as tough as you'd think. And the message cost is just huge. For a system with n processes, you're sending out n-1 requests, and you're getting n-1 OKs back. That's a total of 2 times n-1 messages. Remember that number 3 from our first solution? Yeah, compared to that, this is wildly inefficient, especially as the system gets bigger.
All right, so central control was too fragile, and voting was way too complicated. Let's try a third way, and this one's completely different. Imagine all the computers are sitting in a circle and they're just passing around a single talking stick. That's the idea behind the token ring algorithm.
The rule here is super simple. Only the process that's currently holding the special message, the token, is allowed to enter the critical region. This does a great job of guaranteeing mutual exclusion, and it prevents starvation because the token is always moving around. But it is so fragile. I mean, what happens if the token just gets lost on the network? Or even worse, what if a process crashes while it's holding the token? The entire system could just be stuck waiting forever.
And the efficiency of this one is just fascinating. It's all over the place. If a process gets the token right when it needs it, the cost is basically one message. But if nobody needs the resource, that token could just circle around endlessly, which technically makes the number of messages infinite. It's either super efficient or super wasteful, with almost nothing in between.
So this summary table really makes the trade-offs crystal clear, doesn't it? The centralized algorithm is fast and simple, but it has that deadly single point of failure. The distributed one is tough in some ways, but the message overhead is just massive. And the token ring has crazy variable performance, and it's just plain fragile. As you can see, there's no silver bullet here. Every solution comes with its own major problems.
You know, this brings us right back to our best candidate so far, the centralized algorithm. It's simple, it's efficient, but that one massive problem is still sitting there. What in the world do we do when the coordinator inevitably crashes? Is there a way to fix that one fatal flaw?
And the answer is yes, absolutely. The solution is to have a backup plan for picking a new leader, and that is where election algorithms come into play. When the coordinator goes dark, the other computers need a way to agree on who's the new boss and get the whole system up and running again. Okay, so the first method is called the bully algorithm, and it works pretty much exactly like it sounds. When a process sees the coordinator is down, it sends an election message to every process that has a higher ID number than itself. If any of those bigger bullies respond, they take over the election process. This just keeps going until the process with the highest ID number wins, and at that point, it sends a message to everyone saying, "Hey, I'm the new boss." The biggest kid on the playground always wins.
But, maybe we don't need all that bullying. There is a much more cooperative, more orderly way to pick a new leader, especially if our computers are already set up in some kind of logical ring. With the ring algorithm, when a process detects a failure, it just sends an election message to its neighbor. That neighbor adds its own ID to the list in the message and passes it to its neighbor. The message goes all the way around the ring, collecting IDs as it goes. When it finally gets back to where it started, the original process just looks at the list, picks the highest ID, and sends one last message around to announce who the new leader is. It's a much more civilized election, for sure.
And that really brings us to our final thought for the day. Every single one of these algorithms makes a different trade-off. It's always a balance between simplicity, speed, cost, and safety. There is no one best answer. At the end of the day, it all comes down to a really critical design question for our connected world. When you're building the systems that run, well, everything, what do you care about more? Raw speed or absolute safety? The answer to that question pretty much defines the digital world that we all live in.